Welcome back to this lecture series on pulse width modulation for power electronic converters, and we have been looking at various modules in this course, and here is a quick look at the various course modules. So, one of them is the initially we have seen that we had looked at various power electronic converters, and we looked at the applications of voltage source converters such as motor drive and active front end converters and so on. Then we looked at the purpose of pulse width modulation, namely to control the fundamental voltage and to mitigate the harmonics. Then we looked at pulse width modulation at very low switching frequencies, and we covered topics such as selective harmonic elimination and all that. Then we have been now focusing on, we subsequently covered all this triangle comparison based PWM, where 3-phase modulating signals are compared against a common triangular carrier, and presently we have been discussing the space vector based pulse width modulation. So, this is what we did we started off in the last lecture, and this is the second lecture in this module on space vector based pulse width modulation. So, now as we are aware, the contents of the present module are as given here. The concept of space vector is something we looked at last lecture. We also looked at space vector transformation, how to transform a set of 3-phase quantities into 2-phase quantities. That is something we looked at, and we just started off with space vector based pulse width modulation last time. And so, in this lecture we are going to cover this conventional space vector pulse width modulation in greater detail. We are going to look at this particular method, which is what I would say is the best, or the most popular method among the most popular method among various space vector based PWM. So, one thing I would like to mention at this point of time, generally the term space vector PWM is used by many authors and papers and all that, or simply space vector modulation. When they say that, they normally mean this conventional space vector PWM, which we are going to discuss today. Considering that this is so popular, that is what is generally done. But as far as this course is concerned, space vector PWM would mean a class of pulse width modulation methods. So where the idea of space vector is used in the generation of PWM and so on and so forth, and we would specifically use the name conventional space vector PWM, and we will discuss what this method is shortly from now. And in the next lecture we will be looking at space vector based bus clamping PWM. See, we looked at while dealing with triangle comparison based PWM, we looked at discontinuous modulation methods which cause bus clamping of the phases to different buses. And so, such bus clamping PWM, how to generate such bus clamping PWM from the space vector approach was something that we will discuss in the next class. And in this class what we will also do is we are also going to look at the equivalence between triangle comparison and space vector approaches. That is, whatever you can produce PWM waveform you can produce using triangle comparison method, you can produce the same using space vector approach, and we will be dealing with this in this and probably the next lecture we will deal with this issue. So, some introductory part, at least conventional space vector PWM, how to look at it from the triangle comparison point of view is something we will look at in this lecture, while the bus clamping PWM methods etc. we will look at in the subsequent lecture now. So, as I mentioned even in the last lecture, this equivalence of triangle comparison and space vector approaches have been stressed quite well in the literature, but what is relatively unknown or known to a lesser extent are these space vector based advanced bus clamping PWM methods. So, what is there on the last line here? So, the space vector based advanced bus clamping PWM, here there are what I would say, this is probably what would be the last lecture in this module. We would bring out certain pulse width modulation methods whose PWM waveforms can only be produced from the space vector approach and not using the triangle comparison approach. We will try and establish that space vector approach is more general than the triangle comparison approach, and whatever is the fallout and what advantages it gives etc. and so on and so forth now. So, now over to our present lecture, where we are going to be focusing particularly on conventional space vector based pulse width modulation. So, as I said, this is based on space vector, and I am calling it conventional space vector PWM. This is what is most commonly used among the space vector PWM methods, right. So, to start with, it is a brief recap on the concept of space vector and space vector transformation. So, we had this revolving MMF. So, you apply 3-phase sinusoidal voltages onto 3-phase windings in an AC machine that produces a revolving MMF in the air gap. So, this revolving MMF is an example of a space vector. This is what we had seen in the last lecture too. And now you have these 3-phase windings, and these 3-phase windings you have you can inject currents IR is equal to Im cos omega et, Iy is equal to Im cos omega et minus 120 and Ib is equal to Im cos omega et plus 120 degree. When these are excited by that, what happens is it produces an MMF which revolves at an angular frequency omega e like this. This is what happens. So, this is what we would just see further. So, now this E is an MMF produced by 3 phase windings, but the MMF itself is only on a single plane. It is only on a single plane, and you can say that the MMF's 2 components, one along this direction, excuse me. So, one along the horizontal direction and excuse me. So, this one along this axis, what you can call as alpha, and you can look at it at the other one which is along this axis, which we can call as beta. Now, let us move to the next one and we will see this. So, this is a 3 phase winding. This 3 phase winding, as I was mentioning, produces a revolving MMF. The same revolving MMF can be produced by an equivalent 2 phase winding also, because this MMF that you have here, it revolves on this plane and it has only 2 components. So, any 2 orthogonal axes you can consider. One possibility is to consider the R phase axis itself as one axis, which you can call as alpha axis, and the other one orthogonal to that, which you can call as beta axis. So, whatever is produced, instead of considering these 3 phase windings which are shifted in space by 120 degree, you can probably consider a 2 phase winding which are shifted in space by 90 degrees. The angle between their axis is 90 degrees now, alright. So, you are going to be exciting this by 3 phase currents shifted in phase by 120 degree. Rather, what you can do is you can also you can excite these 2 windings by currents which are shifted in time by 90 degrees, and this way you will be able to produce the same kind of revolving MMF that can be produced by a 3 phase winding with this 2 phase winding and 2 phase currents. So, let us look at it little further now. So, these are the 3 phase axes and these are the 2 phase axes now. I said that the 2 MMFs are equal. When you say the 2 MMFs are equal, one way to put that is you can say the alpha axis component of the MMF and the beta axis component of the MMF are equal in both the cases now. So, the alpha axis component of the MMF is Ni alpha, right, it is Ni alpha as produced by the 2 phase winding. If you consider the 3 phase winding, the equivalent alpha axis MMF is N times IR cos 0 plus N times Iy cos 120 plus N times Ib cos 240, right. And about the beta axis component, so for the 2 phase winding, N times I beta is the beta axis component of the MMF, whereas for the 3 phase winding it is N IR sin 0 plus N Iy sin 120 plus N Ib sin 240. I am sorry, that must be sin, it reads as cos there. So, please change this as sin. So, this is what, because they are along the coordinate, along orthogonal axis. So, this is the cosine components and these are the sinusoidal components here now, right. Now, let us move on to the next one. So, equating the 2 currents, what you have is you have I alpha is equal to IR plus Iy cos 120 plus Ib cos 240, which is nothing but IR minus Iy by 2 minus Ib by 2, and since IR plus Iy plus Ib is equal to 0 or Iy plus Ib is equal to minus IR, you have I alpha is equal to 3 by 2 times IR, as what we saw in the last class. Similarly, you can look at I beta is IR sin 0, which is 0 plus Iy sin 120 plus Ib sin 240. So, sin 120 is root 3 by 2 and sin 240 is minus root 3 by 2. So, you get I beta is equal to root 3 by 2 times Iy minus Ib. So, this gives a space vector transformation, that is you start with currents IR, Iy and Ib. These are 3 phase currents and they can be transformed into 2 phase quantities, namely I alpha and I beta. That is what is going to happen now. So, these are I alpha and I beta. So, that is 3 phase to 2 phase transformation, or what is space vector transformation of 3 phase currents now. So, the same thing has been reproduced here and it can be written in matrix form, if it is convenient to write, so you can write it in a matrix form, that you can I alpha I beta is this matrix multiplied by IR Iy Ib. This becomes the matrix for space vector transformation, right. So, the same way you can handle also 3 phase, you can handle the 3 phase voltages as well, not just 3 phase currents. So, here again you have voltages VRN, VYN and VBN, which are the 3 phase voltages applied onto a balanced 3 phase load RYB, with N being the load neutral, and your V alpha is nothing but VRN cos 0 plus Vyn cos 120 plus Vbn cos 240, and as in the previous case this would add up to 3 by 2 times Vrn. Then you have V beta is equal to this, again an error here. So, V beta would be Vyn cos 30 and then let us say Vbn cos 150 degrees, just as we did last time, or you can also call it as sine 120 and sine 240. So, this is going to be root 3 by 2 times Vyn minus Vbn, and since we have Vrn plus Vyn plus Vbn is equal to 0, that is why this becomes 3 by 2 times Vrn. This is just the same thing, whatever is applicable to the 3 phase currents. Now, we are doing the same thing with 3 phase voltages now. So, you have the transformation of 3 phase voltages into 2 phase voltages. So, V alpha is 3 by 2 times Vrn, V beta is equal to root 3 by 2 times Vyn minus Vbn. So, this is space vector transformation. So, as I just made a brief mention last time, there are also certain other kinds of transformations you can do, means it is pretty similar. Let us say you multiply both of them by certain constant k, that is fine. So, there are some reasons why somebody would want to do that, etc., but this is what we will call as space vector transformation. So, if you find different papers and different textbooks, etc., the definition of space vector transformation could slightly differ from one another. This is the definition that we will use in this course nevertheless. So, you have V alpha and V beta, that is written in terms of Vr and Vy and Vbn in a matrix form as shown here, right. Okay. So, this is now a quick recap on space vector transformation which we did last time. Now, the space vector transformation transforms those 3 phase quantities into 2 phase quantities now, and now we are looking at the 3 phase quantities which are produced by the inverter. Now, the inverter has the 3 terminal voltages R, Y and B, and these voltages can be measured with respect to O, which are called the pole voltages VRO, VYO and VBO. But what is applied on the winding is Vrn, Vyn and Vbn. Let us just look at that little later. So, this is the actual inverter, instead the generic switches have been replaced by IGBTs and anti-parallel with anti-parallel diodes, and now let us say the load is of this shape, it is not there is some load, it is not necessarily inductive or whatever, or you can take it as a star connected winding also. For example, you have R, Y, B are the load terminals and it has a neutral point N. So, R, Y and B are connected to the midpoints of R phase leg, Y phase leg and B phase leg in the inverter, but N is not particularly connected to any of the points in the inverter. So, what you have is a 3 phase connection is what I was just telling you now. So, if you go back here, this VRO, VYO and VBO will have to be converted into Vrn, Vyn and Vbn as indicated here before you can do a space vector based transformation. So, your inverter produces 8 sets of output voltages, 8 sets of output. Why 8 sets of output voltages? You can say R phase, if you take every phase, any phase, R phase, the top device can be on or the bottom device can be on, and therefore, R phase pole voltage can be either plus 0.5 VDC or minus 0.5 VDC as we discussed even earlier. Similarly, VYO, the top can be on or the bottom can be on, VBO also the top or the bottom can be on. Therefore, you have 2 multiplied by 2 multiplied by 2, that is 8 inverter states, 8 combinations are possible. So, the 8 sets of output voltages are possible. So, this 8 sets of output voltages is what we are trying to look at, and you can want to say V alpha is 3 by 2 times Vrn, and Vrn is, it can be expressed in terms of the line to line voltages Vry and Vbr as shown here. Vrn is 1/3 of Vry minus Vbr, 1/3 of Vry minus Vbr. So, that leads to this expression now. Here Vry and Vbr can be replaced, can be written in terms of VRO and VYO here and VBO and VRO here. So, you get half of 2 VRO minus VYO minus VBO, and the same way there is V beta, this is root 3 by 2 times Vyn minus Vbn, this becomes root 3 by 2 times VYO minus VBO. So, what have we done here? We earlier first defined space vector transformation, that is V alpha and V beta, and these are defined in terms of Vrn, Vyn and Vbn. We have now changed that to now we are expressing V alpha in terms of VRO, VYO and VBO, and V beta in terms of VYO and VBO. So, this is convenient because the pole voltages are the ones that are known to us readily many a times, that is once you know the switching state of the inverter, it is very easy to say what the pole voltages are, and the pole voltages can readily be transformed into these things now. So, you have 8 sets of pole voltages and you would expect 8 vectors, but as far as the 0 states are concerned, that is it can be 0.5 VDC in all the 3 phases, that is all the 3 top devices can be on, or it can be minus 0.5 VDC in all the 3 bottom phases, or all the bottom devices, I mean all the 3 phases, all the bottom devices are on. In both these conditions VRY, VYB and VBR are 0, and therefore V alpha and V beta will be 0. In the remaining 6 cases V alpha and V beta are distinct. So, they produce 6 different vectors, and that is what is shown here now. So, when all the bottom devices are on or all the top devices are on, the vector produces a null vector. Other than this, you have 6 different states, and these 6 states are called active states. Why? In these 0 states the load is shorted, there is no transfer of power between the DC supply and the AC side, and the DC side and the AC side, whereas in all the other cases there is some transfer of power between the DC side and the AC side. So, we call them active states, and the corresponding voltage vectors can be called active vectors, right. So, you know in this you would find that not all the phases are connected to the same DC bus. So, some one may be connected to 1 or 2 will be connected to positive bus, and the remaining 1 or 2 will be connected to the negative bus. That is what you find here. And for our space vector transformation, so these 3 phase voltages for any of these would produce a voltage vector of magnitude VDC, and the angle of this voltage vector is what changes from the it differs from inverter state to inverter state. And if you take the active state plus minus minus, where R alone has the top device on and in the Y and B legs the bottom device are on, the voltage vector produced is VDC and the angle is 0. I am measuring the angle with respect to the R phase axis or the alpha axis here. So, see this alpha may be slightly confusing. This alpha you can also use a different terminology, some theta, theta s or something like that. This alpha is the angle that it makes with respect to this particular horizontal axis. That is what I am trying to write down here. Fine, that is for the reference vector, we will come to it a little later. So, there are these 6 active vectors as I was trying to say now. So, what the inverter produces are 8 inverter states, and 6 inverter states produce these 6 vectors, and the remaining 2 states produce this null vector. This is what is now available for you, correct. So, and if you consider a sinusoidal voltage, what do we want the inverter to do? We want the inverter to apply 3 phase sinusoidal voltages on the induction motor. And what do you mean by 3 phase sinusoidal voltages? Now, remember we are in the space vector plane. So, on the space vector plane 3 phase sinusoidal voltages mean a revolving vector as shown by this VREF here. There is a revolving vector. If you transform 3 phase sinusoidal voltages into the space vector domain, what you get is a revolving voltage vector of a constant magnitude, and this magnitude will be equal to 3/2 times the peak value of the sine. If your sine value has a peak of Vm, then this magnitude Vr will be equal to 3/2 times of this thing. Let me also write it down if necessary, it might be useful sometime. So, this is actually 3/2 times Vm, where Vm is the peak phase voltage now, and it rotates at certain angular velocity, that there is some frequency with which it rotates, and that same as the fundamental frequency. So, in one fundamental cycle it will go around that. That is what I wanted to say now, and let us get it little clearer and how does it rotate, etc. So, this position is some arbitrary position that is at an angle alpha with respect to this vector plus minus minus, and this originally stands for your R phase axis. So, what I can say is this vector would have been along the R phase vector when the R phase voltage was at its peak. Of the 3 phase voltages we are considering, when R phase voltage is at its peak and the other this vector would have been like this, and when the Y phase voltage is at its peak, the vector will be aligned along here, and when the B phase voltage is at its peak, it would have been like this, and these are during the positive peak. Similarly, during the negative peaks, when the R phase voltage has a negative peak, the vector would be in this position. So, you get this now. So, it is actually a revolving vector. So, when the R phase has a positive peak, it is here. By the time B phase has a negative peak, it is here. Then it keeps rotating. By the time Y phase has its positive peak, the vector is here. Then it keeps rotating. When the R phase has a negative peak, it comes here, and so it kind of goes on. I think as we go on further and further, the correlation between the position of this vector and the angle of the fundamental will become better. So, what we are trying to say is, first is about the question of voltage reference. Earlier when you try sine triangle PWM, what we do is we use 3 phase sinusoidal modulating signals, and when you look at any other triangle comparison method to the 3 phase sinusoidal signals, we were just adding some common mode component, and we are using some 3 phase modulating signals, though not necessarily sinusoidal. Now, what are we doing? we are taking these 3 phase sinusoidal signals and we are transforming it into revolving vector. If we transform them into the space vector domain, it becomes a revolving voltage vector, and it is a constant magnitude and angle, and this magnitude is, it gives the amount of fundamental, the magnitude of fundamental voltage you want to produce, and this angular frequency is your modulation frequency, gives you modulation frequency, right. So, what we do is, the 3 phase waves becomes a revolving voltage vector in the space vector plane, and in space vector plane PWM you use a revolving voltage vector as the voltage reference. You do not use 3 phase modulating signals, that is one of the differences you start with. In sine triangle PWM or any triangle comparison PWM, you start with those 3 phase modulating signals and you compare them with a triangular carrier. Instead, what you do here is we use a revolving voltage vector, and this revolving voltage vector is sampled once in every subcycle, and the sampled voltage vector gives you the voltage command for the given subcycle. Now, let us say if you sample this is a look, this is how it is going to look. So, it is rotating and it is being sampled. Here I have shown as though, just for illustration purpose, it is getting sampled once in every 15 degrees. So, you find samples every here. So, I have considered that every 15 degrees of the fundamental cycle constitutes one subcycle. So, I am taking my subcycle to be 4 times 6 is 24, 1/24th of the line cycle is what I am taking it to be. It is generally higher, if you look at inverters using switching motor drives at power levels of a few kilowatts or tens of kilowatts, IGBT inverters switch at something like 10 kilohertz or 15 kilohertz kind of frequencies commonly, and your modulating frequency could be 50 hertz. So, if it is 10,000 hertz and 50 hertz, you have a very high switching frequency, and you will really find several subcycles within a half carrier within one cycle now. So, this is anyway just for a purpose of illustration. So, once you have a revolving vector and you sample them, you are going to get samples all around, right. So, sometimes this some sample may fall here, sometimes a sample may fall in this region, sometimes it may fall in this region, here, here, here. So, it is convenient to give some names to these various spatial regions. So, this first spatial region I will call this as, I am writing this as capital, the Roman letter 1 I will use. So, Roman number 1. This is, I would call as various sectors. I would call this as sector 1. I would call this region as sector 2. I can call this region as sector 3, and this is sector 4, and this is sector 5, and this is sector 6. It is just a definition, you can start from somewhere else and whatever. So, now we just let us call them, define them as 6 sectors as I have just mentioned here, and let us go further. So, now this is, I have a particular reference vector which is in sector 1. So, why is it is in sector 1? Because it is between active vector 1 and active vector 2, and this is where the reference vector is, and it makes some angle alpha with vector 1 now. So, how do I produce this? This is the reference vector, that is, this is the voltage that has been commanded. You are supposed to produce so much vector, that is a vector of magnitude Vref, and angle alpha measured from the R phase axis. Vector 1 is same as R phase axis or alpha axis. So, it is there now. So, how do you produce that now? So, you can see that you can resolve it, for example, like that. Let us say from here you draw a line which is parallel to your vector 2, and the line comes and intersects here now. So, you can express this as a sum of this vector and another this vector. The first vector is parallel to V1 vector, and it is a fraction of V1 vector, and the second vector is parallel to V2 vector and is a fraction of V2 vector. So, this vector can be realized by adding a fraction of V1 vector and another fraction of V2 vector. How can you do that? You can do it in a, you can't apply V1 vector and V2 vector concurrently, but what you can do is you can apply V1 vector for certain duration of time t1, and you can apply V2 vector for another duration of time t2. If you do that, what you would get is, you will get VDC times T1 by Ts, this vector plus this vector is what you will get, and T1 plus T2 will be less than Ts. So, T1 by Ts, for example, let us say is 0.6, T2 by Ts could be 0.3, there is still 0.1 is there. So, for the remaining 0.1 Ts you can apply this null vector, which will not add up, which affect the sum of these two vectors. So, this is time averaging, applying active vector 1 for T1 seconds, active vector 2 for T2 seconds, and the null vector or 0 vector for another Tz seconds would give you this kind of, you will, by doing this you will be able to produce this reference vector. As I mentioned in the last class, you can actually synthesize any reference vector whose tip is within this. Let me just draw that, connect those two here. So, let me just draw a line here joining these two. So, you can synthesize any reference vector whose tip falls within this triangle formed by v 1 vector, v 2 vector in this line. So, that is what I am trying to say. You can produce anything there. Okay. Now, you might have your vector falling in another sector. Now, this is sector 2. It can be sector 3 or sector 4. We have considered sector 1, now sector 2. How do you synthesize the vector? The same way. What you do now is, instead of vector 1 and vector 2, you consider vector 2 and vector 3. These are the two closest vectors. And the idea of the two closest vectors is also that intuitively you can see this is what is good. What do you mean by this is what is good? Well, this is what can give you lower harmonic distortion. How can you say this is going to give lower harmonic distortion? Okay. Now, let us say I have taken this vector, So, I want to produce this reference vector. Now, while I want this vector, I am applying here. So, there is a large error vector that is there between these two. There is a, what I am showing in dotted line is the error vector now. So, this error vector is reasonably small when you are considering these two vectors. This error vector is reasonably small when you are doing, as we will see later, this error vector is nothing but, so this reference vector is nothing but the space vector transformation of the 3 phase sinusoidal voltages, 3 phase fundamental voltages. See, we are producing 3 phase voltages, and the 3 phase voltages have fundamental as well as harmonic components. If the fundamental components are transformed, that is what you would get this reference vector. If you subtract the fundamental components from all the 3 phase voltages, you get ripple voltages, 3 phase ripple voltage. The voltage ripple on the along the 3 phases are all transformed into space vector domain, you get an error vector, and so this is the error vector now. You want the error vector to be as low as possible, and in this case the error vector is very high. So, you will find that this is very large now. Another thing that I can tell you, which you can probably verify a little later, when your reference vector is here, you are supposed to apply these two active vectors on the null vector, and if you are applying any other vector, for example, like vector v 1, what will happen is you will see a pulse of opposite polarity. What do you mean by pulse of opposite polarity? Let us take VRY, let us take VRY. When your vector is here, right, or you take for example VYB. If you take VYB, when your reference vector is here, VYB you can see from here is positive, VYO is 0 and VBO is minus VDC by 2. So, the difference between the two, if you take VYB will be plus VDC in this case, and here also VYB will be equal to plus VDC. When the null vectors are, when the null vector is applied, VYB is 0 now, and actually this region falls within the positive half half cycle of VYB. So, similarly, you can look at VRY. If you look at VRY, you will find that this is in the positive half cycle of VRY. Sorry, this will come in the negative half cycle of VRY. On the other hand, excuse me. So, this part comes in the, when this Vref is here, this position of Vref corresponds to certain instant within the negative half cycle of VRY. During that time, if you apply this vector, this is VRY is VDC in this case. So, what happens is you end up applying a positive pulse when VRY is having negative half cycle. That is, 3 phase line to line voltages are there. Consider any line to line voltage, say for example VRY, correct, and VRY should have only positive pulses in its positive half cycle and should have only negative pulses in the negative half cycle. That is what we mean by pulses of appropriate polarity in the line to line voltage waveform. So, if in the positive half cycle of VRY you get negative pulses or vice versa, then it is pulses of opposite polarity. That means a lot of harmonic distortion, a very high harmonic distortion. And whenever you apply a vector like this, for example, you do not apply two vectors which are closest and you apply a vector which is somewhere farther, what you will see is, you will certainly see a pulse of opposite polarity in one or more of the line to line voltages. So, if you want to avoid pulses of opposite polarity in any of the line to line voltage waveforms, you should only apply the neighboring two vectors now. So, if you are in earlier when we were in vector sector 1, we applied active vector 1 and active vector 2. Similarly, when we are moving to sector 2, we should be applying active vector 2 and active vector 3 now, right. So, how do we do that? Once again, as before, you see that you can apply active vector V2 for certain T2, certain duration T2. So, within the subcycle time Ts. So, it produces this is VDC times T2 by Ts. Then you can apply this minus plus minus for that is the vector 3 for a certain other duration T3, and for the remaining duration in the subcycle you can apply the null vector. So, in effect what you will get is you will get this average vector as something that you will get now. So, similarly, if you are going into the next sector, you will be using vectors 3 and 4 and so on and so forth. So, wherever is your reference vector, you will use the two active vectors which are closest to them in terms of the spatial angle, and you will use the null vector. You will use these three vectors to synthesize the the required reference vector now, and this equation gives you the times for which the three vectors have to be applied, the two active vectors and the null vector. Let us say you are in sector 1, Vref vector is synthesized by time averaging of V1 vector, V2 vector and Vz vector. So, Vref vector into Ts equals V1 T1 plus V2 T2 plus Vz Tz, and as you can see that this is a vector equation and there are two dimensions to the vectors, and this actually two equations are there now. If you separate them into the let us say imaginary and real parts, then Ts equals T1 plus T2 plus Tz is the third equation. Together you have three equations and there are three unknowns T1, T2 and Tz. So, you can solve for them. So, if you do that you will get T1 is Vref sin 60 minus alpha by VDC sin 60 times Ts, and T2 by Ts will be equal to Vref sin alpha by VDC sin 60, and Tz is equal to Ts minus T1 minus T2. Remember this VDC comes because that is the length of the voltage vectors. Any active voltage vector is of length VDC for the space vector transformation we have considered here. So, this is what it is now. So, this is how you calculate the times for which the two active vectors are applied and the null vector is applied. Now, the question is there is a redundancy here now. So, the null vector, there are two different inverter states, that is minus 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 where all the bottom devices are on, and plus 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 where all the top devices are on. So, both of these produce the same null vector. The question is which one are you going to use? This is the redundancy in the inverter I have been mentioning to you time and again, and this redundancy is responsible for several of the continuous modulation and the discontinuous modulation methods that we have in the literature, right. So, what do we do? Which one do we use? Conventional wisdom is that better use both. So, let us say if you use only minus minus minus, what will happen? The lower devices are going to conduct for longer time and they might suffer greater conduction loss. Similarly, if you use plus 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 alone, then the top devices might suffer greater amount of conduction loss. So, it might be better to use both of them, for example. Just it's a good option, not necessarily the best option, but it's certainly a good option, and this is kind of conventional wisdom what one can call. So, start from let us say minus minus minus. So, that is a null vector, you are having all the bottom devices are on in all the three legs now. So, you have applied this for some duration of time, let us call it T0, and from here you switch R phase. This is what is R phase indicated here, you switch R phase, go, so that will take you as the red line indicates you, minus 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 becomes plus minus minus now, and you are applying active vector 1. Earlier null vector was applied, now active vector 1 is applied now. So, what you do next is you apply this active vector 1 for some this T1 seconds now. After applying this for the required T1 seconds, you stay here for T1, then you switch the Y phase. The moment you switch Y phase, plus minus minus becomes plus plus minus. So, that is applying the active vector 2 on the load now. So, active vector 2 is getting applied on the load now, stay there for another T2 seconds, and after that what you do is you switch the B phase from minus to plus. The B phase bottom is on and you turn it off and turn on the B phase top. So, it becomes plus plus plus, you come back to the null vector, this is 7. You can apply this for certain amount of time T7. So, in conventional sequence what you do is you start from 0 and you go to 1, 2 and 7. This is what you do in one subcycle. In the next subcycle what you do is you start from here, because you do not switch the inverter unnecessarily, you start from here, stay here for T7 seconds, and from here switch the B phase and go to vector 2, apply this for T2 seconds, and from here switch Y phase and apply vector 1 for T1 seconds, and come back and apply this null state 0 state 0 for remaining T0 seconds. This is the conventional sequence now. So, and what you do also do is you apply T0 and T7 for equal durations of time as indicated here. So, T0 and T7 are equal to 0.5 Tz. You are applying both the 0 states for equal durations of time. This is one picture which shows how the inverter state varies with respect to time. So, the horizontal axis here is time, and this duration is one subcycle time, and this is another subcycle Ts now. So, what you are going to do is you have been given some reference vector, and that reference vector you found that it is falling in sector 1, and therefore, you have chosen to use vectors V1 and V2, and you have calculated the times T1, T2 and Tz using the expressions that were given just before, that sin 60 minus alpha T1 is proportional to sin 60 minus alpha and T2 is proportional to sin alpha, etc. right. So, you do the calculations and you are going to, you are outputting the inverter states as shown here, minus 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 plus minus minus, and then you go to the plus plus minus plus plus plus. This is what I showed here now. So, from minus 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 you are going to plus minus minus and then plus plus minus and plus plus plus. So, that is what I have shown here, minus minus minus, and you are going to plus minus minus plus plus minus and plus plus plus, and the next time you are coming from plus 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 to plus plus minus and then plus minus minus and minus minus minus, and that is what I am showing here now. So, we would call them as 0, 1, 2, 7 and 7, 2, 1, 0, right. So, when you are applying such an inverter state, this is the output of your inverter. When you are doing that, what happens is state means, you know, all the three, there is information on all the three phases are included here. Minus 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 means all the bottom devices are on, therefore, VRO, VYO and VBO are all equal to minus VDC by 2, and from there when you switch to plus minus minus, VRO becomes minus VDC, becomes plus VDC by 2. It changes from minus VDC by 2 to plus VDC by 2. The other ones remain at minus VDC by 2 and minus VDC by 2. And moment you make a transition from plus minus minus to plus plus minus, so now Y phase is switched. Y phase changes from minus VDC by 2 to plus VDC by 2, and B phase continues to be minus VDC by 2. And at the end of this time T0 plus T1 plus T2, what you are doing is you are switching B phase. So, the moment you switch B phase, this changes from minus VDC by 2 to plus VDC by 2, and you have this now, and the next time it is going to switch in the reverse sequence. So, in all this VRO, VYO, VBO are the 3 phase pole voltages. This is the pole voltage, that is the midpoint of R phase leg measured with respect to the midpoint of DC bus VRO. So, this is plus VDC by 2 here and this is minus VDC by 2 here. I am not indicating them, I hope that you can just follow what I am trying to say here. So, this is plus VDC by 2 and this is minus VDC by 2. So, it switches in the sequence RYB in this particular sector, in a different sector it will be different. In this subcycle it is RYB, and in the next subcycle it switches in the sequence BRY. So, RYB, BRY, it keeps on going now. So, in sector 2 the switching sequence will be different, as we will see now. So, if you are doing sector 2, what you would do, you can similarly start from the 0 state, it is plus plus plus, and you can apply this for certain T7 seconds, and from here you switch your B phase, and the moment you switch your B phase, I mean B phase top is turned off and the bottom is turned on, it becomes plus 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 becomes plus plus minus, and you are now applying this vector V2 on your motor or on your 3 phase load. So, this vector V2 is being applied. Let us apply this vector V2 for T2 seconds. At the end of this interval, what you do is you switch your R phase. R phase top is on now, switch that off and switch the R phase bottom on, that will take you to minus plus minus, which is 3. So, vector 3 can be applied for T3 seconds as calculated by those equations which we showed some time back, and you know the similar equations can be used for all the sectors, right. The equations I showed you for sector 1, but the same equations, similar equations can be used for the other sectors also. After that, when you switch Y from positive to 0, it becomes from minus plus minus, it comes to minus minus minus. So, you can switch from plus plus plus, that is 7 2 3 0, or you can switch back 0 3 2 7 as indicated by the red line. So, the blue line, blue arrow marks indicate the sequence in one subcycle, and the red lines indicate the sequence in the other subcycle. So, these two indicate the sequences in the alternate subcycles now. So, as in conventional space vector PWM, the null vector is applied using both the 0 states, and both the 0 states are applied for equal durations of time, though one of them is applied at the start of the subcycle and the other is applied at the end of the subcycle. Your sequence starts from one 0 state and then moves on to the second one active state, the second active state, and then the second 0 state here now. So, this is what is now again I am showing back here as 0 1 2 7 etc. has been outputted here, right. So, you have been given a reference vector, the reference vector is revolving and you are sampling it, and it so happens that the sample falls in sector 1. So, if it falls in sector 1, you are supposed to apply this active vector 1 and active vector 2. Active vector 1 stands for plus minus minus, which is given here, that is R phase positive is on and Y and B negatives are on. Similarly, plus plus minus is the active vector 2. So, you are supposed to synthesize the reference vector by using this active vector 1, active vector 2 and the null vector, and in conventional space vector PWM you use both the 0 states. The remaining time you have to apply the null vector, and the null vector you can either apply minus 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 or plus plus plus. In conventional space vector PWM you use both of them for equal durations of time. So, you have your reference vector, that is, so there is some magnitude Vref and it is certain angle alpha. Using this Vref and alpha, you can calculate this time T1 and you can calculate this time T2, correct, and the remaining time is Tz, and T0 is equal to T7 is equal to 0.5 Tz as I indicated to you earlier. So, all the switching instance can be identified and you are outputting this kind of an inverter sequence now. So, when you are outputting, this is what you are doing in this sector subcycle. In the next subcycle, what you are going to do, you are going to have a reference vector. We are considering the steady state situation. So, in the steady state situation, what do you have? The reference vector will have the same magnitude. Between here and here, what would have happened is the reference vector would have rotated by a further angle of omega Ts. So, it rotates by a further angle of omega Ts. So, here you will have the same Vref, but your alpha would have changed to something like alpha dash, and consequently what will happen is this T1, T2 etc. would slightly change. So, if you observe this, now this I have given as a T1 dash, that is because alpha has changed to alpha dash. Similarly, T2 is T2 dash because alpha has changed to alpha dash, something like alpha plus omega Ts, it has changed to that, and the remaining null vector time is also some Tz dash, and that is equally divided between 7 and 0 as T7 dash and T0 dash. So, you have this kind of inverter state being outputted now. So, you start in the space vector approach, what you are doing is you are starting from the 3 phase, I mean you are instead of 3 phase sinusoidal voltages, you are starting from revolving vector and you are sampling the revolving vector, and from the sample of that revolving vector for that particular sector you are calculating the dwell times T1, T2 and T0 and T7, and then you are outputting the inverter states like this. If you are outputting the inverter state, what happens? If you look at the voltages at the three load terminals, VRO is like this as given by the red line, and VYO is as given by this green line here. I have been using green instead of yellow here just for better visibility, and again VBO is given by this line, and it is minus VDC by 2 here and plus VDC by 2 here. This is your output now, right. So, this is what we are now producing from the space vector domain. So, let us look at this now. So, this VRO is here, and this VRO is sometimes minus VDC by 2 and sometimes it is plus VDC by 2, and it has some average value which is between the two, minus VDC by 2 and plus VDC by 2, and considering that plus VDC by 2 is for longer duration and this average is indicated by this dashed line, this is closer to plus VDC by 2, right, it is closer to plus VDC by 2, and the average voltage here and the average voltage in the next subcycle are going to be slightly different, but that is too different. So, I am just kind of ignoring it here. So, I am just drawing it as a horizontal dashed line. I have shown you some dashed line. The dashed line is VRO average, the average value of VRO in this subcycle and in this subcycle, right. Okay. Now, that VRO average, MR star is the equivalent modulating signal, or it is a scaled version of VRO average. So, this VRO average is some k times VDC by 2, right. You divide that VDC by 2, so you will get this k. So, this MR star is the scaled version of this now. So, if that MR star is compared with the triangular carrier as shown here, compare this MR star with a falling ramp as shown here, then the two will intersect at the switching instant. Similarly, whatever is this MR star, the scaled version of VRO average, you compare it with a rising carrier, they will intersect here at the what is this switching instant. So, this is the reverse direction. Instead of starting from your revolving reference vector and sampling and calculating T1, T2 and then outputting the inverter states and producing VRO, VYO, VBO, one could have also started with this MR star and this MY star and MB star, and compare this MR star, MY star and MB star with the triangular carriers as shown here, and you could have identified the same switching instance by such kind of comparison. So, that is why we say that this conventional space vector PWM can also be implemented from the triangle comparison approach. So, the same PWM waveform can also be produced from the triangle comparison approach. So, where you have to use this MR star, MY star, MB star, we are only looking at 2 subcycles now, right, and there is some small difference in MR star in this and here, we are ignoring that right now. So, if you look at all the subcycles, it will have some wave shape, and this wave shape of MR star will not be sinusoidal, it will be some sine plus some common mode added to that now. Similarly, MY star will be some sine plus common mode added, will be a phase shifted version of MR star by 120 degree, MB star will also be a phase shifted, and so you can call this MR star, MY star and MB star as equivalent modulating signals. So, this VRO, VYO, VBO are the pole voltages, and what you have seen in the dashed line are the average pole voltages, VRO average, VYO average and VBO average. These are pole voltages averaged over a subcycle, and MR star is the scaled version of VRO average, and if this MR star is compared with this kind of triangular carrier, you can identify the switching instance of each phase independently. So, this is what there is some similarity between the two. So, the same PWM waveform can be produced either from the space vector approach or through the triangle comparison approach. Let us go one step further now. So, I said average pole voltage, right. I just did that kind of graphically there. Now, I am doing it mathematically here. So, average pole voltage. So, what is average pole voltage? Sometimes the instantaneous pole voltage is plus VDC by 2, sometimes the instantaneous pole voltage is minus VDC by 2 for every phase now. You take R phase in sector 1. So, what happens in sector 1 when the 0 state minus is applied, the average pole voltage is minus VDC by 2, otherwise I mean the pole voltage is minus VDC by 2, otherwise VRO is always plus VDC by 2. So, if you look at VRO average, it is plus VDC by 2 multiplied by T1 plus T2 plus T7 divided by Ts and minus VDC by 2 multiplied by T0 by Ts. Of course, T0 is equal to T7 is equal to 0.5 Tz in conventional space vector PWM. So, this is the average pole voltage for R phase now. How about the average pole voltage for Y phase? So, Y phase top device is on during the inverter states 2 and 7. This is plus plus minus, this is plus plus plus, and during the inverter state 0, that is minus minus minus, Y phase bottom device is on. Similarly, in the inverter state 1 plus minus minus, the bottom device is on. So, VYO is equal to minus VDC by 2 during the intervals T0 and T1, and VYO is equal to plus VDC by 2 during the intervals T2 and T7. Therefore, you have VYO average is VDC by 2 times T2 plus T7 upon Ts minus VDC by 2 times T0 plus T1 by Ts equals VDC. So, this is what is your average pole voltage for Y phase now. Is it okay? You can see there is a clear difference between VRO average and VYO average. Here this T1 is here in the positive, and here that T1 is shifted to the negative 1. Therefore, you can certainly see that VRO average is quite positive here, whereas this VRO average is lower here. And here you can see that VRO average should certainly be positive. Why? T0 and T7 are equal. So, you can just cancel the two terms now. Let me just do that cancellation for you here. So, these two terms can just be cancelled off. So, the average pole voltage for R phase is VDC by 2 times T1 plus T2 upon Ts, which is very positive. Why is it positive? Because we are in sector 1, and sector 1 is very close to the R phase axis. So, that is R phase axis, I mean the when R phase has its peak voltage, the voltage vector is really along positive, this thing is along the R phase axis now. So, VRO is the R phase is going close to it, it has just crossed its peak actually. So, that is why it is still very positive now. And you take VYO, see this term is positive and this term is negative, and here again you have T0 and T7 are equal and there can be cancelled off in case of conventional space vector PWM. Let me do that cancellation here also, so that things become clear now. VBO average you can very clearly see that is negative now. Why should it be negative? Because we are in sector 1, and sector 1 on one side is bounded by the positive R phase axis, and the other side it is bounded by the negative B phase axis. So, in sector 1 R phase is close to its positive peak and B phase is close to its negative peak, and this is because B phase is close to its negative peak, we have VBO average is negative now. And how about VYO average? On R is going close to positive peak, B is close to negative peak, Y should naturally be close to its 0 crossing. In fact, the center of the sector 1 is what would correspond to the 0 crossing of Y phase. Now, let us say you have this. So, this is VDC by 2 times T2 by Ts, this is minus VDC by 2 into T1 by Ts. You have a special case, let us say particular case where T1 is equal to T2. When will you have T1 is equal to T2? When alpha is equal to 30 degrees, you will sin 60 minus alpha is equal to sin alpha is equal to sin 30. So, when alpha is equal to 30, you will have T1 is equal to T2 and VYO average will be 0. The center of R phase, I mean the sector 1 corresponds to the 0 crossing of Y phase. So, at that point your average pole voltage is 0. But let us remember these average pole voltages are not sinusoidal quantities, they have sine plus some common mode added to that, and one can consider the scaled version of this. I can write this VRO average as some VDC by 2 into MR star by VP. So, this VDC by 2 VP can be taken as the inverter gain, and VRO average is proportional to MR star, which is the equivalent modulating signal of R phase. VYO average is proportional to MY star, the equivalent modulating signal of Y phase, and similarly VBO average and MB star. So, these terms VDC by 2 VP, this term can be regarded as the gain of the inverter now. So, this is about our average pole voltages and the equivalent modulating signals that I had derived here. I showed you some average pole voltage, I just derived an expression for this average pole voltages there, and the scaled version of the average pole voltage is MR star, and if this MR star, MY star and MB star are compared with these kind of triangular carriers, you can get the same switching instance. So, what you can do is this can also be produced by doing from the triangle comparison approach. You can start from MR, MY and MB, add some common mode. What is that common mode? We still do not know. If you add suitable common mode, you can get MR star, MY star, MB star. Once you get that common mode component, you can compare with triangle carrier and you can produce the same PWM waveforms that conventional space vector PWM produces, right. So, before going there, let me just underline the fact that VRO average plus VYO plus BBO average is not equal to 0. That means there is some common mode component there, or their scaled versions MR star plus MY star plus MB star is again not equal to 0, that is some scaled version is there. So, the sum of these 3 is 3 times the common mode voltage, again the sum of these 3 is 3 times what you can call as MCM. So, let us take it from here. So, what is this MCM we have to find out. So, this VRO average I on VIO average and VBO average I have discussed them only for one sector. This in sector 2 and sector 3 etc. also you can write expressions for VRO average, VIO average, VBO average etc. I would leave that as an exercise to you. In fact, if you sketch VRO average over the entire thing, you can subtract it from the sinusoidal component and you can find out what the common mode component is. That is, to sketch VRO average over the entire cycle for example, and similarly VIO average and VBO average, I would leave that as an exercise, and from there the determination of the common mode component can also be an exercise. But anyway, we will determine the common mode component starting from the other side. What did we do now? We started with sine triangle PWM here, I am sorry, we started with space vector PWM and we calculated the dwell times of the inverter states, and we outputted the states and we came up to this pole voltage. Then we considered the average pole voltage, and then we showed that if you compare the equivalent modulating signals with triangular carrier, also you can produce this now. Let us start from the other side. Instead of starting from space vector PWM, let us start from sine triangle PWM. So, this is a figure which is actually produced from Pawan Kumar Hari's MSc engineering thesis on comparative evaluation of PWM, which is on comparative evaluation of different PWM techniques, and this evaluation is in terms of harmonic distortion and switching losses. Some work of Pawan Kumar Hari's thesis we will be discussing in the later lectures when we are into going into evaluation of line current and switching loss. So, now let us look at the sine triangle PWM. What we are going to do is looking at sine triangle PWM from a space vector point of view. So, the sine triangle PWM, what you have is you have 3 phase sinusoids and you compare them with a triangular carrier. I am just considering one carrier here, and for simplicity the value of the triangle will change, I mean the modulating signal will change from one half carrier to another half carrier. I am just ignoring that here for simplicity. So, sometimes this is called regular sampling at every carrier interval, or it is called symmetric sampling, because the switching instants are equidistant from this peak and that peak. That is, let us say this peak you have, now R phase will switch here and R phase will switch there. This distance and that distance are equal. So, you call this as symmetric sampling sometimes, alright. So, you have this carrier as shown here, falling carrier and rising carrier, one carrier cycle, and you have taken some VR is equal to Vm sin omega t and Vy Vm again Vy, some value of Vr, Vy and Vb. So, and their actual values. So, you have considered some numbers for Vm and omega t and you get these values now, and you compare them, you see that R phase switches here, Y phase switches here, B switches here, similarly B, Y and R, and you look at the inverter states. This is inverter state 0, that is minus minus minus, this is inverter state 1, that is plus minus minus, this is inverter state 2, that is plus plus minus, and here it is plus plus plus. So, the 0 1 2 7 and 7 2 1 0 is almost same as what you got here. 0 1 2 7 and 7 2 1 0 is very similar to what you got there, is very similar to what you got there, right. Now, what is the difference? That is what we need to focus on now. The difference right now I would point out that you can see that this 0 and this 7 are not applied for equal durations of time. This 0, for how long is it getting applied? It is applied for a duration proportional to this difference between plus Vp and the R phase modulating signal. Similarly, this 0 state 7 is applied for a duration proportional to the difference between Vb and minus Vp, and these are not equal. This vertical distance and this vertical distance are not equal, and therefore, these two horizontal durations are not equal, T0 and T7 are not equal. That is the main difference between sine triangle PWM and space vector PWM now. So, you once again you start from 0, 1, 2, 7 you can go around, and you have active vector 1 applied and active vector 2 applied and null vector for the remaining time, and therefore, once again there is time averaging and you produce some average vector Vref now, and this is in one sub cycle. You look at all the half carrier cycles over the entire cycle, you will have average voltage vectors applied like this. That is once you will have this, in the next half carrier cycle you see you may have another average voltage vector whose magnitude is the same, but the angle is changed by omega ts. So, if you look at the average voltage vectors produced over different sub cycles, this is what sine triangle PWM does. This is what sine triangle PWM does, very similar to space vector PWM. In space vector PWM you will talk in terms of the sectors. So, your reference vector is between vector 1 and vector 2. In here in sine triangle PWM, relative values of 3 phase sinusoids. If MR is greater than MY, the modulating signal of R phase is greater than that of Y, which and MY is again greater than MB, then it would correspond to this sector. Similarly, every sector actually corresponds to some particular kind of relative values. So, MY is the middle value here, MR is the middle value here, MB is the middle value here, and so on and so forth. The 6 sectors correspond to can be determined based on the relative values of 3 phase sinusoids. I will deal with this better when we do this bus clamping PWM in the next class, and you go through the same switching sequence, pretty much the same switching sequence as in conventional space vector PWM. The only catch is T0 and T7 are not equal, that is the only difference. Now, the simple question is how do you make them equal? That is all that we are going to deal with very quickly. So, you have 3 signals, you call them M max, M mid and M min, you call them M max, M mid and M min, right. So, now you want to add some common mode. So, M max star, M mid star and M min star, all common mode added, you get this now. What you want is, you want the null vector time to be equal. For the null vector time have to be equal, then M max star should be equal to minus M min star. Both should be equal in amplitude, but opposite in sign, or M max star plus M min star is equal to 0. This leads to the condition M max plus M min plus 2 MCM is equal to 0, or MCM is simply equal to minus 0.5 times M max plus M min, or 0.5 M mid. So, the common mode component should be equal to 0.5 times M mid. This is what you have to do. In every half carrier cycle, you will have M max, M mid and M min. You take 50% of M mid and add it as common mode component, and that will give you equal division of null vector time. So, sine triangle PWM would get effectively changed to conventional space vector PWM. This is very easy for you to implement. Once you have implemented sine triangle PWM, this is a very, very small change, and by doing this you can get 15% higher voltage as we got in the third harmonic injection case. We will discuss probably this in a little greater detail in the next class. So, it gives 15% voltage, and also it gives equal null vector time, and if 15% higher voltage means you get the advantage of 1/6 third harmonic injection now, and in terms of harmonic distortion, it gives you whatever benefit that 1/4 third harmonic gives you in the third harmonic injection there. We will discuss this in some detail when we go into the line current ripple analysis now. So, this is the common mode component that I told you. So, what kind of common mode component gets added now. So, what you will exactly find is, you will find that your common mode component will go like this. This is M mid. If you simply look at M mid, your R phase will be the M mid up to 0 to 30 degrees now. So, then the next one will be 90 degrees. So, your M mid, if you draw, it will be like this, and your MCM will be half of this. Your MCM will be simply half of this. This will be a common mode component. We will do more of this in the following class. So, thank you very much for being with me, and these are some references which I indicated the last time. These are some additional references which will be very useful for you. So, thank you very much, and hoping to meet you again in the next class. Thank you.